Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Martin, and I'm going to be talking about the cost of adding protection to enterprise networks. And I think logically this talk could have gone before the other one because it motivates it really well. And the fundamental premise is that people do want fine-grained access controls, and I'm going to take from a security standpoint in a little bit more of a paranoid environment than maybe you guys are used to, and say people already want these, and so they're approximating them with traditional solutions like firewalls, for example, or VLANs, and they're not working. Not only are they not working, they kind of break the networks. I mean, they have these really negative effects of networks. So what I'm going to do is I'm going to step through some examples, anecdotal examples that I've experienced where you're trying to foist protection into existing networks. You've got these bad effects. And then if you guys are a good audience, I'm going to very, very quickly talk about some research we're doing in this area to address it. So I do have a bias. So I worked in a national lab for a couple of years. I come from the security side of things, and so I'm quite interested in commercial networks or financial networks or medical networks or national lab networks. And I'm not going to throw out terms like gigapop or anything that are kind of these small internets. I'm going to really focus on we want to secure maybe one building or maybe less than 50 switches or something like that. And so that doesn't mean to say that these principles don't scale beyond those, but I'm really going to try and ratchet it down to something easy to talk about. So I'm going to pick on what I think that are three problem areas. There were four here. I had isolation here and I dropped it because of time constraints, and I'm kind of glad I did because I actually learned a lot in our breakaway section. So I'm going to start with inflexibility, and I'm going to do it by example. And so I've run into this twice, and this is kind of an idealized network environment what this came up with. And so let me just really quick explain. You've got a bunch of hosts that are connected to an L2 switch that's connected to a firewall, and you want to do fine-grained access controls, right? You want to do something that a NAC will do today. And I'm going to do it with pretty standard traditional techniques. And the properties I want for my fine-grained access controls, I don't want someone to be able to land on a computer and enumerate the hosts. I don't want someone to be able to sniff the traffic. And it's surprising, and maybe it's a function of my background, how often this happens. So let me talk about a very common way people set this up. So the first thing is very common. Okay, well, we've got firewall rules. We've got other networks here and other networks here. We want to make sure these people can only talk to certain parts of the network. Traffic can only come in if it's part of an established session. Standard stuff. You got this problem with ARP, right? So ARP is unauthenticated, and ARP has a race condition, right? So all these guys share an ARP cache, which means that if I send a gratuitous ARP, I can poison the ARP cache and I can get your traffic. This is pretty standard. Another thing I can do is ARP gets sent to broadcast, right? This is something you can't really solve with VLAN unless you do implicit tagging by IP address, which means, again, I can enumerate the hosts by whoever's ARPing. So what they traditionally do is they'll turn off ARP and they'll kind of chisel in MAC addresses at these various points. Right? So I've got my cafe dead beef and my cafe dodo, which are my MAC addresses. I'm chiseling them into end hosts and into the router. Of course, we've got static IP addresses because we've got a static ARP cache and we've got firewall rules, so we don't have any DHCP. Right? So notice we have ARP, which is an indirection point. We have DHCP, which is an indirection point. Indirection points always mean flexibility in computer science. We're turning them off. Right? On top of that, switches have been pushed into services security. So they weren't built for security. They were built for efficiency so you don't have collisions. And I don't know what the state of the art is today, but 2 years ago, if you invented a whole bunch of MAC addresses and sent them out, you could overflow the CAM and they would fail open, right? Another thing you could do is say, I know all these machines probably came from the same vendor. The MAC addresses probably came from the same vendor. I can probably guess that we have the same, top level bits. So I'm going to go ahead and fiddle with the bottom, and I'm going to forge a MAC address. The switch is going to learn where I'm coming from, and then I can get somebody else's traffic. So the way that we did it is, if you have like a cat 2 cage, you turn on port security, which says, I've got a physical port, and I'm going to chisel a MAC address into one of these physical ports. Okay, so let's talk about flexibility. So I've got all this configuration state where I've chiseled all this topology information into it. So the way networks have always worked is very adaptive, right? Like you've got these consensus agreements. I've got something that will route, and I've got something over here that will route, and if something bad happens, we'll find a new route, and we'll kind of come to a consensus, and it works. And there's no similar thing for security configuration state, right? If something changes, it's broken, essentially, right? And so you've kind of got this problem, right? If you move a machine, you can have something that's bad, which nobody can talk to each other, or something much worse that everybody can talk to each other, right? You undermine a security policy. Now, one of the principal causes of this is, indirection points, which is kind of this paradigm for achieving flexibility, are completely unauthenticated, right? And so they're just removed or turned off. And so I'm going to come to this later, but I want to put it now. As you'll see that there are MAC addresses in a lot of these configuration states, which you get no aggregation. They actually chew up a lot of memory, right? Now I'm going to talk about the loss of redundancy. So normally when I talk, I want to like pick one or two things I want people to walk away from, because I think that's all people normally do walk away from. And one of them is from maybe this slide or maybe the next slide. And this is, we engineer our networks very often around security policy. Okay? And it's not, because here's the point. The point is, it's not because of the Candy security model. It's not because of the perimeter security model. It's not because we've got one way to talk to the world. So we engineer choke points in a lot of secure networks for internal communication, right? And the question is, why? So I'm going to give you guys a lot of conjecture. I'm not sure. I've talked with a number of people, and I've got two general reasons. One of them is, what Needham and Schroeder would call a psychological acceptability. I've got some guy breathing down my back, right? And he says, okay, Martin, I want you to make this network, and I want fine-grained access controls, and this person can talk to this person, but not using this protocol and everything else, right? I'm an IT administrator. I'm like, listen, I understand PICs, and that's about it. You guys are all going through one firewall, right? It's much easier to reason about, and it's much easier to verify. So I've got a lot of I've got 4 topologies right now, and all of them have all the securities in one central place. They're in star nodes, and this is for internal traffic, not for just kind of perimeter security traffic. Another problem is proxies. And the reason I call this a problem is it's not often that someone will turn on application level routing, right? So if I've got policies that are application protocol specific, like, SMTP must go one way and HTTP must go one way and you guys must go through proxies, the only thing you can really do is put them through the same choke point, right? Unless you're going to have to do some layer violation and route them somewhere else, which some people do, and this is actually supported in some routers. I've never actually seen it turned on. I like to point that there's a lot of existing solutions out there, and they seem to kind of exacerbate the problem. One of them is like, I'm going to sell you a $200,000 machine, and it's got a bunch of proxies on it, and it'll look into anything. It'll look into IM, right? ICQ, it'll look into email, it'll look into NFS. And another one is for network and mission controls. A lot of times you buy one bridge and you put it in your network, and that's it. And there's obviously kind of a scalability problem, and I argue now, and I'm going to argue more later, that this doesn't necessarily have to be the case, right? You don't have to build your topology around your network structure. So the last one is filtering. Kind of in the security world, if you've got a resource and you want to control access to it, you normally do one of two things. One thing is you make a list of everybody that can access this resource, right? And then every time someone comes to get access to that resource, you check your list, and if they're on the list, you let them do it, right? Of course, the more people you have that are accessing this list, the bigger the list gets, and the longer the check takes, right? So today, filtering is done exactly on the data path, right? In most cases, right? Which means that every packet that comes in, a packet comes in, and I've got to check this pretty complex rule set to say, whether I'm going to let the packet in or whether I'm not going to let the packet in. And so of 3 administrators actually I've talked in the last 2 months, all of them have had problems with running out of ACL space, and they're generally because they're trying to whitelist MAC addresses. And so, in some cases, especially the case that I talked about beforehand, where you've got a switch, and in the switch you've chiseled in all these MAC addresses anyways. It doesn't really make sense to have forwarding tables which aren't really being used anyways and filters anyways, because it just kind of comes down to connectivity. So actually, I'm going to talk briefly about a proposal that we're working on to mitigate the situation. And what we'd like to do is kind of construct a new way to think about a network architecture. And it falls very much under the 4D principles of having a control plane and a dissemination plane and a different data plane. And And it seems very obvious. Today you're trying to realize a security policy in a bunch of different mechanisms. Sometimes they're very stringent security policies, and sometimes they're not. And so the idea is can you have an arbiter, a central arbiter, some server that understands this entire policy? And you go and you ask this arbiter once on the control plane whether you can have access, and it'll give you access on a per flow basis, on a per route basis, the granularity of a route. And once you get that, you can communicate, right? So now we've kind of solved the proxy problem because you can get different routes for different applications that you request. You solve the filtering problem because this is off the data path. This is kind of control path, the way you're doing it. So I've got like an action sequence, then one more slide, and then I'm done. Okay, so this guy kind of knows what security policy you were trying to approximate with all your different firewalls and so forth. And so you don't want to have anybody to be able to talk to each other except for this guy until you authenticate first. So we're replacing ARP, we're replacing DHCP, and all these unauthenticated indirection points by one, right? People are trying to approximate this with IPsec today. I think it's a great discussion on whether this is the right technology. I definitely think IPsec is the way to authenticate. I'm not sure it's the way to grant access, right? Right? So I got our global policy. I authenticate. I'm Martin. And I say I want to host a service. It's not that important. Somebody else authenticates, and then they can request access to me. And the way that we do requesting access is I send my first packet, right? If it's a TCP packet, it's going to have the ports, for example. It's going to be who I'm going to talk to. You're going to know that because I've already authenticated, right? So now you do the permission check, the only time you do the permission check, right? This isn't like a per packet thing. This happens once. The access is granted in the form of a route. So when I grant you access, I'm not adding you to an ACL. I'm giving you I'm setting up a route in the switches that can be used for communication, right? So this can be bad for all sorts of reasons that we can argue about. I mean, I would argue that it actually scales very well. I would argue that the state requirements are less than exist today, and normally I get very unpopular when I say that. And it's a discussion I'm willing to have, but I'll push it off to the questions. So just to kind of reiterate, there's a lot of problems. I've focused on three. One of them is the flexibility, which you kind of lose because you're taking this configuration state, you're kind of chiseling it into machines. You don't have any distributed way of updating it, right? You've got redundancy for two reasons. Number one is, you put in a lot of switches, you can undermine security policy. Also, you've got proxies that you require routes to go through, and instead of being application routing, you can kind of just put these in one place, even though they're being used for internal communication. And so here, you've got one policy. I can take an arbitrary number of switches. I just throw it in, and all they do is they enforce routes, and so they don't undermine it. And there's only one permission check, which kind of makes sense. I mean, it's kind of more the capability way of doing things, where you've got a permission check, and then once access is granted, you've got your real fast data path, which you can do it at gig speeds. And so that's it. And this is a 300-point question mark, right? So this isn't an image. This is actually font. So. Any questions?
I'll ask you the question you wanted to answer. What evidence do you have that it's not?
So, let me predicate all this stuff, but this is actually pretty preliminary, and we built this central server that contains the policy, and it'll calculate a route, and it'll do a permission check, and it'll grant you access. And it operates on the order of 60,000 requests per second, which, I mean, you were mentioning previously that, I mean, you see about 10,000 per second. We looked at the Berkeley topology, and I think at max it was getting was 2,000 or 8,000 or something, but it was well over less than we can do. Nick?
You mentioned lack of redundancy is one of the problems, and I'm sort of wondering
You got
why
one.
this single box that's granting access isn't
Yep.
similar type of problem. And actually, more specifically, I'm sort of wondering why you're pushing data towards a single box rather than pushing configuration out from that box
Right.
to the distributed node.
This is
Putting a policy in.
Yeah, absolutely. These are two very good questions. So the centralization question, I'm going to give you kind of a security answer because I like it the best. And a lot of the work that we're trying to do is actually consolidate trust, and instead of having it in like a DNS server, which if I subvert, I own you, and a DHCP server, which I subvert, I own you, we put it in one box, and I know where to put my guy with the gun, and then if you want replication, I'll replicate that box 5, 10, as many times as I want. And so, yes, if you bomb that exact building because I wasn't smart enough to put it in different places, you've got a problem. So I agree that you are introducing a central point of failure, but I mean, it's only logically centralized. You can decentralize it. The second question is actually harder. I mean, so I kind of give you this spiel, and I don't think there's any scientific answer here, but the spiel is you don't necessarily need to do these filtration checks on every packet that comes through, right? So instead of doing some complex policy and saying, listen, it doesn't matter whether you're logged onto the network, and it doesn't matter where you're sending the traffic, you're going to have all this configuration state to deal with it, right? So it's a matter of consolidation.
But some firewalls do this where, basically once the rules pass, like you get to the context, and then the rest of the flow is good. You don't have to check everything.
Yeah, and this is what cut-through routing does. Yeah, absolutely. I mean, and this is what cut-through routing is. I'm going to bless it, then I'm going to stick you in hardware. It's a simplification of that, for sure. But there's another problem is we want very minimally trusted elements. Very minimally trusted, right? So right now, the only thing you do is I've got a hardware flow table, and a packet comes in, and I say, okay, are you part of the flow? And I send you out. I mean, this is about as simple. And we're building it right now, in Verilog with very little code. So there's a simplicity argument, and I'm not sure it's you buy it, but it's definitely kind of one of the catchphrases.
Is the network the right place to be implementing security at all?
Absolutely, 100%.
Okay, I mean, I subvert a box, and then, that box can go and it can talk to some server, and then through that other server, I can try and subvert it and talk to something else. I mean, it's just...
No. So I've got two answers to this, if you'll indulge me. The first one is I think people are already putting it in the network because people that control networks want control of data as much as they want control of connectivity. So you've got a lot of middle boxes in there just because they have introspection. I mean, they're kind of trying to solve this confinement problem game where, I've got documents going back and forth, and I'm going to pay somebody to go ahead and do this full proxy. So a lot of this is already going in. And you've got a funny trust model if you're saying, listen, I'm just going to give it to anybody that can plug into the network, right? So depending on your threat model and your trust model, if your threat model is, I want to stop rogue laptops and I want to stop people from tinkering with their laptop, you probably want to push it in the network. And now this is complete conjecture, and you guys can quote me, but it would probably be wrong, is I think a lot of the reason is they want to be able to have full control over whatever they're managing instead of trusting it on the end. So, I mean, this is definitely a very kind of, security-oriented perspective. Networking guys generally hate it. I think that there's going to be some grounds in the middle where you have some trusts for the authentication, maybe virtual methane, so you attest the protocol stack. But yeah.
When the central authority grants the route, does it have visibility of the performance on every leg and failovers and failures at the current time?
No, but only because when we did this work and we did the prototype, it was because we were focusing on a security problem. We're saying, can you do this securely? Can you build default connectivity to the central guy, and can you get the topology to him, and can he communicate with other people and authenticate switches securely? So that's what we focused on. The route computation right now is pretty dumb. It's like, I'm gonna compute 1 or 2 or 3 routes depending on how much redundancy you have, and that's it, and nothing goes in. That doesn't mean you couldn't very easily kind of, put in, link latencies or anything else you wanted to. But right now it's solely a security architecture, right? But this is because it's a research.
I might have missed something, but are you suggesting that you would change all of the sort of the operational aspects of the switches and such, so they would maintain like flow tables of what is, to represent the routes that you have authorized, and presumably those routes time out at some point based upon re-auth or something like that. But at least those things could then look the same, I suppose.
Yeah. So this is it. So and this was really I was kind of at a dead run when I was going through this. The idea right now is you actually build kind of these bumps in a wire that you put between switches, Ethernet switches, and they use the switch learning to enforce the isolation. And so between switches you have these little dongles that will enforce the flows, and they do it kind of by themselves. So we build them. But then you're not using any of the security functions except for possibly VLAN for more fine-grained, per port access.
So you're building dongles essentially to sort of do the operational management, and making sure that no flows, no routes are used that aren't authorized.
That's exactly right.
So operationally, you have to do that all.
Excuse me? No, the control plane. Well, I mean, I'm still trying to kind of fit this into the 4D whole. the control plane is this central server which you authenticate with. It makes the decision. It does the permission check, and then you've got your data plane which you set up the routes on. Yeah, I think this makes the most sense in the context that I was describing, where you've got a fairly closed. I mean, so people are trying to approximate these things today. I mean, you get boxes that do this. They do fine-grained access controls, and the only way you can really do that, I mean, you've got a choice. I can do forwarding tables and filters, or I can just do, per flow routes, right? And this is definitely optimized to the latter. I don't think this makes much sense in a very, very open environment, because you're going to be setting up these. You just kind of go back to ATM, right? Right. And I understand that this is very much. It looks very much like ATM, and the question is, can we do it, today in existing operational networks that use Ethernet and IP, and provide the same guarantees with kind of a security flare? Cool. Okay. Thanks, guys.